Okay, thanks, Luca. So today I want to talk about joint work that I've done with Ben Andrews. And this is sort of some nice application that's kind of somehow just fallen out of our work on gradient bounds for parabolic equations. And I'm going to sort of start off very slowly and give you lots of easy examples, but so you know that I'm actually going somewhere with that. This is the conjecture that we want to solve, and it's talking about the distance between the first two eigenvalues of this Schrödinger operator equation. And it's the conjectures on what's the closest these two can be. So to tell you what the equation is, it's just a Laplacian with some potential V, capital V, in a domain omega. And here I'm going to impose Dirichlet boundary data. But this problem also makes sense if you pose Neumann boundary data or mixed boundary data. And you can also look at these things on manifolds with boundaries or compact manifolds. So it's this elliptic operator, and so there's eigenvalues and eigenfunctions. And they satisfy an equation, and the eigenfunctions also satisfy the Dirichlet boundary data. And sort of very basic spectral analysis tells you that there's this increasing sequence of eigenvalues, and this sequence goes right up to infinity. There's no accumulation points, and we label them. So the smallest one we call lambda 1, the second smallest one we call lambda 2. So I sort of was planning to motivate this in terms of minimal surfaces and geometric problems, but sort of this morning Bill talked a lot about eigenvalues and eigenfunctions and really used them. So I guess you can sort of see that, you know, knowing how big your eigenvalues are is kind of useful in a geometric setting. But this is just a completely straightforward linear PDE here. Okay, and so what I'm going to be really interested in is this fundamental gap. So it's also called the spectral gap. And this fundamental gap is also really of interest to people working in statistical mechanics, because it tells you how fast a given state is sort of going to decay to what they call the ground state, the first eigenfunction. And so they call this gap this sort of excitation energy. And so I guess where Steve sort of waved his hands and said parking garages is the application, I can sort of wave my hands and say quantum tunneling, which means I don't know so much about it, but apparently that's what people are using it for. Okay, and the problem of when you start thinking about what effect the shape of the domain has on the eigenvalues, sort of got quite a high profile by this paper by Kac, where he asked, can you hear the shape of the drum? So this elliptic problem is also called the fixed membrane problem. And the idea is, if you know exactly what the spectrum is, do you know what the shape of omega is? So I'm going to go sort of in the opposite direction to that and ask, if you know something about the shape of omega, what can you say about the eigenvalues? And the kind of things that people are looking at when they say knowing something about the shape is they look at the diameter, they look at the volume. So if you fix the volume of omega, you have the Faber-Crane inequality telling you what the minimal eigenvalue is. You might look at the boundary curvatures. If it's a manifold, you might look at something like a lower bound on the Ricci curvature. And then, you know, use your imagination. You can look at different numbers of connected components or different ways in which they're connected, dimension. But, okay, that's all work that other people are doing. What I'm just going to say that omega is convex and has some diameter which we call capital D. And omega doesn't have to be strictly convex, it can have corners. And this is the sort of most simple toy example that will take you back to first year, and not first year of graduate school either. If we have an interval and we have a constant V, so our PDE just becomes a differential equation like this. And you can solve this. It's sort of clear that the first eigenfunction is going to look like this. It's given by a sine function, and you can explicitly write down the eigenvalue. And it goes on. You can look at the second eigenfunction. The second eigenvalue is now 2 pi on d squared plus v. And you see how this goes. Yeah. So it's sort of very clear what the fundamental gap for this one is. It's lambda 2 minus lambda 1. And it's given by exactly the quantity in the conjecture, 3 pi squared on d squared. Okay, so I wanted to put this example down because our sort of whole philosophy here is that somehow we try and characterize the behaviour of this problem on a domain by the behaviour of a one-dimensional analogue of the problem. And so what we find is, in some sense, the worst behaviour of the general problem doesn't get much worse than the behaviour of this one-dimensional problem. And also, so you can sort of see this picture, and in some ways you have a good idea of what's going on with the general problem. So in particular, you can see that the first eigenfunction is positive, as Bill mentioned. The second eigenfunction changes sign. And if you look at a ratio of the first two, so by which I mean phi2 divided by phi1, you can sort of imagine, if you look at the picture, that it's going to satisfy a Neumann condition at the boundary. And that's quite general. But of course, for the sort of more general problem, there's more to the story. So things that you shouldn't think carry across the general problem are that the symmetry of the second eigenfunction. So that means that the maximum is equal to minus the minimum. So that doesn't hold in the general case, and it kind of causes lots of technical problems when it doesn't hold. You can get much better results not much better results, it's much easier to get results if you assume that this holds. Another thing is, if you look at this first eigenfunction, you can see that it's convex. That doesn't hold in the general case either, but we do have log concavity, sorry, it's concave. So if we look at log of this first one, then it's concave. So it's a little bit weaker than concavity. So just to show you that this one-dimensional example wasn't some sort of outlier, it wasn't the 3 pi squared on d squared wasn't just something that holds for the one-dimensional one. Here's sort of a second example. And these things are sort of exactly as they are in Courant and Hilbert. If you look, okay, you've got this rectangle with a long side and a slightly shorter side. And if you look at the eigenfunctions are sort of products of the eigenfunctions on the interval. So now this phi nm is indexed by 2 positive integers, and we get an associated eigenvalue. And so if we look at the first eigenvalue, that's going to be when both n and m are equal to 1. And, oh, I forgot the v there. There should be a v. Sorry, maybe I can use this thing. I just want an excuse to use this thing, actually. Here we go. Okay. And if we assume that A is the longer side, then, oh no. It's just over the and, it's not over the equation, so that's okay. So maybe I'll write my plus v up here, just in case something comes up there. Okay, so it's very clear what the gap is for this one, 3 pi squared on a squared. Now, the diameter for this rectangle is just the diagonal, so a squared is equal to d squared minus b squared. And so what you see is that you can get this as close as you want to 3 pi squared on d squared just by sort of shrinking b down and sort of making this into a very long and skinny rectangle. Okay, so Van den Berg was looking at these kind of things, especially at these rectangular domains and their high dimensional analogues, and he sort of observed that many convex domains have this bound from below on the fundamental gap. He was working in statistical mechanics, and this is also conjectured by Yau and Ashbal-Ben-Gurion quite independently of Van den Berg and each other. Okay, now I don't want the V's. There we go. So this is the sort of formulation more like the one used by Yau and Ashbal-Ben-Gurion. They wanted to have quite a general domain, a convex domain, and a convex potential V. And yeah, so the conjecture is that 3 pi squared on d squared is the best you can get. Okay. So people have been working on this problem, and it's really been solved in one dimension. So in '98, Ashbal and Ben-Gurion had a look at a sort of similar case when your potential is symmetric and single well, so it's not necessarily convex. And I don't know if you can see the little picture I made there, but you can have corners and things like that. And single well means that at first it's non-increasing and then it's non-decreasing after it gets to the bottom of the well. And yeah, and the conjecture as stated was proved by Levine for one dimension. Okay, and he doesn't have any symmetry assumptions. But because V is convex, it's also going to be single well too. Okay, now in high dimensions, people have sort of got a collection of lower bounds which are really too small. So there's this paper by Singer Wong, Yau and Yau, and this paper really sparked off a lot of interest in the subject. It's really quite influential. And they got this lower bound pi squared on 4 over d squared. In the case that you have this symmetry of the second eigenfunction, so the maximum is equal to the maximum of the second eigenfunction is equal to minus the minimum of it, then you get something a lot better. You can get rid of that factor of 1/4. Yeah, that was if they assume that. And that was actually shown without this assumption by Yu and Zong a little bit later. And they used essentially the same techniques, but they really worked hard on making a kind of symmetrization and yeah, and that's kind of where it's got to. There's a real technical difficulty to get anything better than that, and the technical difficulty is that you've got to get something better than log concavity for your first eigenfunction. So in their proofs, when you get something like a second derivative of log phi1, they kind of throw it away because they've got a sign on it. And you need to get something better. And so more recently, John Ling has got a lower bound in which he assumes that he has some non-zero bound on the second derivatives of log phi1. Okay, so you can see by the 31 over 50 that it's kind of a really hard work that he's doing here. And if you put say phi1 when you know it in the one-dimensional case in, you can see that this is still going to be a long way off optimal. And there's also another paper by Yau where he's also makes some assumption on this second derivative of log phi1. Okay, so, and I should also mention that the conjecture's also been solved for some highly symmetric domains. So Burgess-Davis and independently Banuelos and Kroger sort of showed that it holds in the case where you have symmetry with respect to both x and y axes on a plane. And I think Ashbal Ben-Guri have also solved it for us, a radially symmetric domain. Okay, so I'm going to try and sketch out our proof of this. I've got a bit of time and it's quite simple, so feel free to ask questions if it's not clear or I don't define things, because it should be quite clear. Yeah, so this is what we do. We take our problem on omega and we want to relate it to a one-dimensional problem on an interval. Okay, so it's clear what the Laplacian becomes just a second derivative. Okay, it becomes an ODE. We've got to define a new potential because, okay, original potential is defined on omega. So we have some new potential here, which is V, I call V tilde. So all the tilde quantities are on the interval. And we take an interval that's got length given by the diameter of our original domain. Okay, and mu I are now the eigenvalues on this interval. Okay, and I should tell you how the two potentials are related. I've got this sort of nasty technical condition, but really you can ignore that if your original potential is convex. So if V is convex, then this quantity here is positive. So you can just take any constant V tilde and that'll satisfy this. So yeah, so for the purposes of proving a conjecture, just assume that V tilde is constant. Okay, so what we need to do is really improve this log concavity estimate. So the original estimate that the first eigenfunction is log concave is from Braskamp and Lieb, and there's also some nice proofs by Curvature and Caffarelli and Spruck. So that's kind of good, but we need to do better. And so what we have is this quantity here, which is equivalent to log concavity, we show that it's bounded from above by log phi1 tilde. So phi1 tilde is the first eigenfunction on the interval. So if you sort of remember what log phi1 looks like, so phi1, can I make this pen thin? Right, okay. Okay, so, yeah. Okay, so this is phi1 here. So log phi1 is going to look like this. Okay, and it really goes down to minus infinity at the boundary. Okay, so you can see that at the turning point there, it's not telling you anything new. It's just telling you that this is 0. But we get something a lot better. So this is labels. This one's V1 and this one's log V1. Yeah. But we get sort of something huge as we go out towards the boundary. Okay, so we take this and sort of things are always more fun if you've got a parabolic equation rather than an elliptic equation. So with the eigenfunctions, we can quite easily make a parabolic equation. We just look at a sort of a time-scaled, we look at a time-scaled eigenfunction. So if we look at, so if u is equal to e to the minus lambda it phi I, then ut is going to equal minus lambda r u. So we can just slot this into our eigenvalue equation and get a nice parabolic equation. Right. Okay, and this guy satisfies the same boundary values as the original one. Okay, and now I make a new parabolic equation by taking the ratio of these two. Is something in the way here? So if you remember U1, the first eigenfunction is positive, so this is well defined on the interior. And U2's got this change of sign. So V has its own parabolic equation, like this, and you can see that any dependence on the potential has sort of been swept away here. And then we want to make an oscillation estimate for V. So what we do, we find that V has this time, the oscillation of V has this time scaling given by the fundamental gap on the interval. Okay, that's mu2 minus mu1, fundamental gap on the interval. And I'm going to show you the proof of this. Okay, so we sort of have this strategy which we call coordinate doubling. So we start off with, say, an elliptic or parabolic equation on omega. And from that, we define a new quantity which is defined on omega cross omega. And then we're going to use a maximum principle on this new sort of doubled equation. Okay, so my new quantity is Z, which is V at Y minus V at X, minus this psi. Now psi's barrier. And you can see that my space variable is just given by the distance between Y and X. So this barrier is really defined on it's just in one space variable. And we're going to try and show that Z is less than or equal to 0, and that will be the oscillation estimate. And we do this by making a maximum principle. Okay, so we can write down an evolution equation for Z. This is dz dt. And then we've got second derivatives. Well, we start off with second derivatives of V, but we can write second derivatives of V in terms of second derivatives of Z plus some terms that are like second derivatives of this barrier. Okay, here A is a sort of some positive semi-definite matrix, which I sort of need to deal with my cross-derivative terms. Okay, then we have psi t, and then sort of some lower order terms. Okay, so the lower order terms that look like gradient of V I can write as ones in gradient of Z plus psi prime terms. Okay, and if I choose a barrier where the psi prime is positive, then this sort of gradient of log phi1 is just taken care of by our log concavity estimate. So we can replace this term here by a derivative of phi1 tilde. Okay. Okay, and then we apply the maximum principle. So we start off with the barrier that makes Z 0 or less than or equal to strictly less than 0, let's say. And we assume that Z attains a maximum somewhere at some time, some positive time, a maximum of 0, I should say. And because this is going to be a spatial maximum too, we know that the second derivatives of Z will be negative semi-definite, so this trace term we can let go. And because it's a spatial maximum, we sort of know that our gradient of Z will be 0 too, so we can get rid of that as well. Okay, so we end up with this term, which is just a one-dimensional PDE in the barrier. And so we want to choose a barrier that makes this 0 or really strictly less than 0. But if you look at this equation here, it's kind of exactly like our V equation, but in one dimension. Okay, we've got a psi t, a second derivative, and psi prime, and then a gradient of log phi1. Okay, so that sort of tells us that we should choose a barrier that's like a ratio of the one-dimensional eigenfunctions. And if we do that, we'll get a 0 here. Okay, so that's exactly our barrier we use, and we get a 0. And you know, there's a little bit more work here because we need to really show that this is strictly less than 0. And we also need to work a little bit hard on the boundaries to make sure that our boundary values are satisfied in our initial values. But here we're working with these one-dimensional eigenfunctions, and they're really neat. You can do everything you want with them, really. They make sort of this nice L2 basis, and it's really easy to hammer together. Well, not really easy, but sort of straightforward to hammer together some barrier that does what you want it to do. Okay, so that's our oscillation estimate for V. Okay, because we have the maximum principle, we can say that if Z starts off being 0, it remains 0. Okay, the next step is, this is just restating that lemma 1, the oscillation has this time scaling, but because V, we constructed it quite concretely out of these time-scaled eigenfunctions. So V itself has its own time scaling. Okay, this is V. Okay, so V here's got 2 time scalings, and there's only one way that this is going to work. So the oscillation of V is given by the oscillation of this ratio of eigenfunctions. Okay, here the oscillation is just a spatial oscillation. Okay, so I can take these terms, these time-dependent terms out the front, and I get just this simple expression for the oscillation. Okay, so I can put that on the other side of my inequality from the lemma and say, okay, this oscillation of phi2 over phi1 time scales like this. But okay, so the oscillation is just a constant in time. It doesn't change with t. So if this term in here, in the square brackets, is positive, then as t goes to infinity, this all becomes 0. So the oscillation has to be 0 to begin with. Okay, so that means that my eigenfunctions, my first 2 eigenfunctions, are just a linear multiple of each other. Okay, now that's not on. These eigenfunctions really have to be orthogonal. The second eigenfunction has to change sign. So there's a contradiction. So what we find is that this term in square brackets, it has to be negative. Okay, and so that's really the gap estimate there. So mu2 minus mu1 is the fundamental gap on the interval, and we worked that out. That was that easy example I had at the beginning. Okay, that's just 3 pi squared on d squared, and so we're done. And yeah, that's kind of how it goes. But I didn't really use that my potential capital V is convex. The only point I used it was sort of here, when I said we know what this is. And in the case that we don't have a convex potential, all this goes through. We just need to use that kind of awkward condition on the one-dimensional potential relating to the original potential. But we still get this bound on the fundamental gap. So that's sort of a more general result. This is this sort of awkward condition on the potentials. There's sort of explicit examples where you have some non-convex V with 2 wells, what they call a double well example. And in those cases, you can sort of cook up things where the gap goes to 0. So this might be sort of a bit vacuous. But there are cases where you've got a non-convex V and there's a non-zero gap for the one-dimensional equation, and so this really will tell you something there. So that's sort of what we've done. We've got the gap conjecture, and we really use this parabolic maximum principle. So there's sort of 2 elements really. We didn't have all this worry about symmetry because we're sort of imposing our own symmetry. We're sort of working this Z function's got is sort of highly symmetric. And so maximum, when you're at a maximum of this, you're sort of getting a lot somehow. You're sort of, yeah. And yeah, log concavity was a really important thing. So if we don't have an improved log concavity thing, all we go back to is being a sort of a nice proof of the Yuan-Zhong estimate, the pi squared on d squared. And we've got this non-convex result as well. So that's it. Thanks for your attention.